Hello, everyone. This is lecture number 3 of the physical chemistry chapter Specific Heat of Solids. The subtopic of this lecture number 3 is Einstein's theory. So, before starting the Einstein's theory, we should have an idea about a perfect crystal system. A perfect crystal is an idealized solid where atoms or molecules are arranged in a continuous and flawlessly repeating three-dimensional pattern called a lattice. And it should have the following characteristics. Number one, the crystal lattice should have zero crystal defect. We know all about the crystal defects. That means in the interstitial positions, some parts, the lattice points are missing. So the defects may be metal excess type, metal deficient type, or the Schottky defect on Frankel defects. There should be no defect in a perfect crystal. Number one. Number two, the structural motif or basis is replicated uniformly in all directions with no boundaries or distortion. That is, it infinitely repeats in all directions. That means the atoms or the motifs or the lattice points are deployed very much regularly, and they are having no boundary or no distortion, and they are being repeated in all directions uniformly. Number three, this is the next last one. The atoms are treated as quantum harmonic oscillators bound to their equilibrium lattice sites by forces following the Hooke's law. That means all the atoms are oscillating by following the rule of a quantum harmonic oscillator, where the Hooke's law is very much followed. The law is F equals to minus K into X. K is the force constant, X is the displacement, whereas F is the force, and the negative sign, that means the movement of the atom is opposite to the force of attraction in the direction. Now move on to the Einstein's equation for heat capacity of solids. So Einstein made the following assumptions in order to derive heat capacity of a monatomic and perfect solid crystal. Look here, the term perfect solid crystal comes. So we know what about a perfect solid crystal, what about its characteristics. So what types of assumptions were made by Einstein? Number one, there is no rotational, translational, and electronic mode of energies associated to its total energy contribution. So, if there is no rotation, if there is no translation, or even no electronic mode of energy, then only one mode is left, and that is the vibrational mode. So, the atoms in the crystal lattice undergo only oscillation or vibration from their equilibrium positions. Number three, there is no interatomic interactions between the atoms. So, none of the atoms are disturbing any other atom. So there is no interatomic interaction due to their oscillation or vibration. Number four, each atom has three independent vibrational degrees of freedom. So, likewise, the Dulong-Petit's law, the vibrational mode here is having three degrees of freedom for each atom. And last, finally, number five, a solid is an aggregation of atomic oscillators, and each of the oscillators are vibrating with a common mean frequency nu. So here is the assumption where it is said that all the atoms having a mean frequency when during their oscillation, and that is nu. This assumption is very much important because this may have some disputes in explaining the calculated values, that is the experimental results. Now move on to the different vibrational energy levels. So Vi is the vibrational quantum number, and the energy expression for each vibrational energy level is epsilon Vi equals to Vi plus half h nu. So Vi is the quantum number. So if Vi is 0, then it is V0, and in V0, Vi, you should put 0 in place of Vi, then you will get the energy, 0 point energy, or the energy of the ground state, and that is half h nu. So epsilon 0 is half h nu. Similarly, epsilon 1, that is the energy of the first excited state. By following this equation, you put 1 here in place of Vi, then you will get 3 by 2 h nu. If you place 2 here, then you will get 5 by 2 h nu for the second excited state. Similarly, for the third one, 7 by 2 h nu, for the fourth one, 9 by 2 h nu, and etc. Now, if Vi is equal to I, then it is the energy of the ith excited state, and this energy is I plus half into h nu. So, These are the energy distribution for each vibrational energy level. So the quantized vibrational energy levels are having energy from the 0 point energy to the ith excited state, which are actually respectively starting from half h nu to I plus half h nu. The average one-dimensional energy of an oscillator has been calculated from the concept of partition function. It is epsilon bar, and it is nothing but equal to h nu over exponential h nu by kt minus 1. So this is the formula. Okay, epsilon bar equals to h nu by e to the power h nu by kt minus 1 average for one atom. For 1 mole of a substance, so if there is 1 mole of a substance, then there are overall Na number of atoms. So the total energy must be Na into epsilon bar, okay, equals to Na into the expression of epsilon bar. If all the three possible directions of vibration are taken into account, so each atom has three modes of vibration along x-axis, along y-axis, and along z-axis. So for in order to get the total energy, we have to multiply this Na into epsilon bar with 3. So it is 3 Na into epsilon bar, and the result is 3 Na h2 by e to the minus e to the power h2 by kt minus 1. So this is equation number 1, where we get the expression of U on the basis of Einstein's assumptions. Therefore, the heat capacity of a solid, Cv, at constant volume, has the expression we all know, del U by del T at constant volume. So let us differentiate the expression of U with respect to temperature, keeping the volume constant. So if we do so, then we have to differentiate this overall parameter 3 NaH nu by this one, 3 NaH nu by this one with respect to temperature at constant volume. So what is the result of this differentiation? The result of this differentiation is Cv equals to 3 NaH nu into del t of 1 by e to the power minus e to the power h nu by kt minus 1, because h and nu are constants here. So we have taken these two constant terms out of the differentiation portion. So only the function of t remains here inside this differentiation expression. Now, so this is e to the power h nu by kt minus 1 whole to the power minus 1. So that is why minus 1 is taken here. Now, since it is minus 1, then another minus 1 would be added for differentiating this one. So minus 2. Okay. Now, if this one is done, then we have to differentiate this one. So differentiation with respect to t of what? Now, e to the power h nu by kt minus 1. Now, differentiation of this one is possible, but this one is not possible because this is a constant, so the value is 0. So only we have to do this one. So what should be the result? Just the result should be e to the power x. That means e to the power h nu by kt. Then again you have to differentiate h nu by kt with respect to t. So here, by merging this minus 1 with overall this term, it becomes minus 3 Na h nu. Then this e to the power h nu by kt minus 1 whole to the power minus 2. This one here repeated. Now, this e to the power h nu comes out after differentiation here, and then you have to differentiate h nu by kt with respect to temperature. Okay, and this is definitely again will be a negative result. With h nu by k are constants, and 1 by t becomes 1 by t squared. That means the differentiation result should be minus h nu by kt squared. So minus h nu by kt squared here, and minus form is given here as minus 1. Okay, this minus minus would cancel each other. As a result, it becomes 3 Na h nu. Then this term e to the power h nu by kt minus 1 to the power minus 2. Then this one e to the power h nu by kt, and then finally this one h nu by kt squared. So we have written it here like h nu by kt divided by t squared. And after having just a little bit arrange them, it it is having the form thrice Na. Then this k This k, what is this k? Actually, this is h nu by k. Okay. So h nu is here, h nu is here also. So you can have h nu whole squared, but k does not have any square value. So in order to make it k squared, you have to take 1k in the numerator. You have to add 1k in the numerator. In this way, if you take 1k here in this position, in the numerator position, then all these things like h, nu, k, and t will be squared. So it is h nu by kt whole squared. Then this one e to the power h nu by kt minus 1 is here, and this e to the power h nu by kt is here. Okay, since this is minus 2, so it goes to the denominator. This way you have got the expression of cv like this, because Na is Avogadro's number, K is Boltzmann constant, so it is Na into K means the universal gas constant R. So instead of Na into K, we have written here R. All the other terms remaining the same. This way you get equation 2, where we have the expression of heat capacity of solids. This is the Einstein's equation number 2. So we have equation number 2 here. So if you are taking the note, then don't write it twice, because for going to the next slide, I have repeated here. But during your note writing, you should not write this twice. Okay, you just start from here. Now, if h nu by k, here h nu by k, if you write this as theta epsilon, okay, theta epsilon is the characteristic temperature. If you write this as theta epsilon, then the equation 2, what would it become? It would become 3r into theta epsilon by t whole squared. Here h nu to the e to the power theta epsilon by t. Here e to the power theta epsilon by t minus 1 whole squared. So this equation becomes thrice r theta epsilon by t whole square, e to the power theta epsilon by t, e to the power theta epsilon by t minus 1 whole squared. This way you get the equation number 3. So theta epsilon is called the characteristics Einstein temperature, which has definitely the dimension of temperature. This is equation number 3. And equation number 3 clearly states that Cv is a function of theta epsilon by t. So if you take 3r, then all these things are function of theta epsilon by t. So Cv is equal to thrice r into some function of theta epsilon by t. Okay, and theta epsilon depends only upon the value of that common mean frequency nu. Okay, and this frequency is the characteristics of that particular solid. And here the expression of theta epsilon, which is equal to h nu by k, is given in the number 4 equation, because with the help of equation number 3 and 4 we have to find out the value of cv. And if you plot according to equation number 3 cv against t, then you will get this type of equation theoretically, which at this point, which would support the Dulong-Petit's law. And this point means T should be very high, that means more than 300 Kelvin. And in that case, Cv almost equal to 5.9, that is thrice R. Okay. And if you move on to T tends to 0 in these points, in that case, Cv also tends to be 0. And here, nu can be measured from the experimental values of T and Cv with the help of, as I have already said, equation number 3 and 4. And the failure of this Einstein's theory is that if the lower range of temperature in the lower range of temperature, the calculated values fall more rapidly than do the experimental values due to neglecting the interatomic interactions. So that was the main drawback, where we have neglected the interatomic interactions. Not only that, there is common mean frequency nu, The new value also needs to be a little bit rectified, which you will find in case of determining the device t cubed law. Okay, now do some numerical problems. The first problem is for aluminium. The theta epsilon value is 240 K. So you have to calculate Cv for aluminium on the Einstein model at 50 Kelvin and also at 240 Kelvin. So what is the equation? Cv equals to thrice r epsilon theta epsilon by t whole squared. Then this one, just put the values. Okay, r 1.987 calorie per Kelvin per mole and theta epsilon 240 Kelvin, because it is given already 240 Kelvin. Now number A, if T is 50 Kelvin, then this is the expression. Just put the values. In case of R, 1.987. In case of theta epsilon, 240. In case of T, 50. The same things are being reflected here also. And the result is 1.148 calorie per Kelvin per mole. And number B, if you put just 240 in place of 50, like A, then you will get this value, 5.52 calorie per Kelvin per mole. Now, the second and last question of this lecture. At 150 Kelvin, the Cv values of copper is 4.7 calorie per Kelvin per mole. What is the value of theta epsilon of copper? Okay. So the Einstein equation, what is the equation? We know the equation. This one is the equation. Now, R, we know the value of R, and the value of Cv is given, which is 4.7. Now, theta epsilon by t, just assume it to be x. So, what is the form does it take? 3 into the value of r into, in place of theta epsilon by t whole squared, we are writing here x squared. And here, in place of e to the power theta epsilon by t, we are writing here e to the power x. And here also e to the power x minus 1 whole squared. So, x equals to theta epsilon by t. So, the expression gets this form. Look at the previous one. 4.7 equals to 3 into something something. So x squared into e to the power x divided by e to the power x minus 1 whole squared must be 4.7 divided by 3 divided by 1.97. And the value is 0.7885. Okay. Now you have to solve this equation. There is no particular way out of solving this equation or particular procedure to solve this equation. You have to apply the trial and error method. Okay. You have to take some arbitrary values of x, then which one would match the right hand side would be accepted. So if you put 1.5, then this one gives the value 0.829, does not resemble. If you put 1.7, then it goes further nearer to this value. So if it it is 1.7, then it is almost nearer to this value. So little bit increase the value of x, put x equals to 1.71. In that case, this left hand side becomes equal to 0.788. So the value of x, that means theta epsilon by t, is 1.71, and from there you can calculate the value of theta epsilon as 256.5 Kelvin. So that's all for this lecture. Thank you and have a nice day.